What if, within the intense radiation environment surrounding Jupiter, there existed an icy world that might still harbor life? That world is Europa, Jupiter's fourth largest moon. Smaller than Earth, yet concealing a secret that could change the course of scientific history. Using the highest resolution images ever obtained from Galileo, the Hubble Space Telescope, and recent close flybys by Juno, scientists have revealed a shattered icy landscape so-called chaos terrain. Not the quiet, static impact craters seen on our own moon. Instead, Europa's surface is crisscrossed by a dense network of massive fractures and dark reddish streaks stretching thousands of kilometers across the ice. Even more striking, Hubble has detected towering plumes of water vapor rising hundreds of kilometers above the surface, suggesting that the ocean beneath the ice may be directly interacting with space. This could provide an ideal environment for life, similar to ecosystems found around hydrothermal vents on the ocean floor here on Earth. If we were to find life on Europa, then what would happen? Europa orbits Jupiter at a distance of only about 670,900 kilometers, and this very position places it at the heart of an invisible engine of destruction, the Jovian radiation belts. Jupiter possesses the strongest magnetic field of any planet, roughly 20,000 times stronger than Earth's. And this magnetic field traps high-energy charged particles, electrons, and ions, creating an extremely intense radiation environment. Europa lies deep within this region. Measurements from the Galileo mission and subsequent observations show that the dose of ionizing radiation on Europa's surface can reach approximately 5 sieverts per day. The average surface temperature is estimated to be around -160 degrees Celsius, and in dark regions or during extended nights, temperatures can drop to nearly -220 degrees Celsius. At these temperatures, water freezes hard as rock. Chemical reactions slow to the point of nearly stopping, and every familiar biological mechanism we know becomes unable to function. It is a world where heat is almost absent. Europa's atmosphere, if it can be called that, exists only as an extremely thin layer. Observations indicate that it is composed mainly of molecular oxygen, produced not by biology, but by a process known as radiolysis. High-energy radiation from Jupiter bombards the surface ice, splitting water molecules into hydrogen and oxygen. The lightweight hydrogen escapes into space, while the heavier oxygen remains trapped in a tenuous gaseous layer. The surface pressure of this atmosphere is trillions of times lower than Earth's atmospheric pressure. It is essentially a vacuum. Oxygen is present, but not to breathe, not to protect, and not enough to support any kind of ecosystem. Europa's surface thus becomes a realm with no stable liquid water, no climate cycle, and no natural shield against cosmic radiation. Even the most extreme microorganisms on Earth, organisms that tolerate high radiation or extreme cold, would struggle to survive for long if directly exposed on Europa's surface. Yet high-resolution images reveal that its surface is almost entirely lacking large impact craters, an unusual feature for an icy body that has existed for billions of years. This suggests that the surface is young and continuously being renewed. It shows that the surface is not always the most important place. Sometimes, conditions so hostile as to be unacceptable are themselves a sign that the answers lie elsewhere. In Europa's case, all scientific evidence leads to the same stark and clear conclusion. If life exists, it must be hidden from the surface. That question opens a door to a realm beyond direct imagery, but one where scientific data is becoming increasingly clear. A global subsurface ocean, dark, deep, and possibly the only place on Europa where life has a chance to exist. During the Galileo mission in the 1990s, magnetic field measurements taken as the spacecraft flew past Europa revealed an anomaly. Jupiter's magnetic field was distorted in a way that could only occur if a layer of electrically conductive material existed inside Europa. After ruling out other possibilities, scientists arrived at the most reasonable conclusion: a layer of liquid salty water rich enough in ions to induce electrical currents when interacting with Jupiter's immense magnetic field. Most current studies now converge on a relatively consistent scenario. Europa's outer ice shell has an average thickness of about 15 to 25 kilometers, beneath which lies a salty ocean reaching depths of roughly 100 kilometers, and deeper still may be a layer of silicate rock in direct contact with the water. This structure is critically important because it allows water and rock to interact, a key condition in many hypotheses about the origin of life. The scale of Europa's ocean far exceeds intuitive imagination. With Europa's radius of about 1,560 kilometers, a global ocean tens to hundreds of kilometers thick implies an immense volume of water. Estimates suggest that the total amount of liquid water on Europa may exceed all the water in Earth's oceans combined. Earth, despite being called the blue planet, actually has only a very thin layer of water covering its rocky surface. Europa is the opposite. Water may be the dominant component by volume, with ice serving only as a sealed outer shell. Europa's surface is almost entirely devoid of large impact craters, indicating that it is geologically young. Stretched, fractured, and overlapping ice bands reveal that the ice shell is not a rigid, immobile block, but a system capable of movement, cracking, and refreezing. These features are difficult to explain if what lies beneath is nothing more than solid ice, extending tens of kilometers downward. By contrast, they are consistent with an ice shell floating atop liquid water, able to bend, slide, and restructure over time. Salts detected on Europa's surface, including sodium and magnesium compounds, are thought to originate from the ocean below, transported upward through icy geological processes. This suggests that Europa's ocean is not completely isolated. It is an open system to some degree, open enough for chemistry to occur, open enough for essential components to be redistributed over long geological timescales. That thick, cold ice shell may also shield the ocean beneath from Jupiter's intense ionizing radiation. If the surface is a place where biology cannot survive, then, beneath the ice, the ocean may be a far more stable environment. One where complex molecules have time to persist, interact, and evolve. The existence of a global subsurface ocean on Europa forces us to reconsider Earth itself from a different perspective. On our planet, sunlight plays a central role in all major ecosystems. But if liquid water can exist stably for billions of years, if chemistry is sufficiently rich, then life, even in simple forms, may not require a sky, may not require day and night, and may not require photosynthesis. However, water and time alone are still not enough. A vast ocean, if completely still and cold, would ultimately become a chemical graveyard. To remain liquid, to drive chemical reactions, energy is required. The turning point came from observations by the Hubble Space Telescope. In observing campaigns that began in 2012 and were analyzed in greater depth in the years that followed, scientists detected unusual structures rising above the limb of Europa. They were not reflected light, not optical noise, but elongated columns of material extending roughly 100–200 kilometers above the surface. Spectral data showed that their primary component was water vapor. In the near-vacuum environment around Europa, water disperses rapidly, yet its signature was distinct enough to be distinguished from any other phenomenon. What makes this discovery significant is not only the existence of the plumes, but their intermittent nature. They do not appear continuously like steady jets, but are observed only at certain times, often coinciding with specific positions of Europa along its orbit around Jupiter. This suggests that the plumes may be directly linked to tidal stresses within the ice shell, when Jupiter's gravitational pull becomes strong enough to temporarily open fractures. In other words, these are not permanent conduits, but natural pressure valves that open only under the right conditions. The most widely proposed mechanism to explain this phenomenon is cryovolcanism, ice volcanism. On Europa, volcanoes do not erupt molten rock, but instead expel liquid water, ice, and salt, rich solutions from beneath the crust. When pressure builds within shallow water reservoirs or liquid pockets, trapped beneath the ice beyond what the overlying shell can withstand, material is forced upward through fractures and escapes into space. Under extremely low temperatures, the water rapidly changes phase, forming clouds of vapor and fine ice that can be observed from afar. Importantly, physical models indicate that the source of these plumes may be connected to the subsurface ocean, even if not all of them can be confirmed to originate directly from depths of tens of kilometers. Some scenarios suggest they may arise from shallow lakes trapped within the ice, sustained by the ocean below. Regardless of the specific pathway, the central point remains unchanged. Europa's ice shell is not an absolute barrier. Its plumes transform the ocean into a natural sampling system, lifting material close to space without any human intervention. Theoretical analyses suggest that material within the plumes may carry dissolved salts, ions such as sodium and magnesium, and potentially simple organic molecules. While such molecules are not evidence of life, they are crucial pieces for assessing the chemical richness of Europa's ocean. On Earth, environments rich in salts and chemical complexity are precisely where microbial life readily survives and adapts. However, Europa's plumes are not detected consistently, and confirming their presence remains a challenge. Some observations have failed to reproduce the phenomenon, leaving questions about their frequency and stability unresolved. For this reason, Future missions such as Europa Clipper are designed with a clear focus, not to search directly for organisms, but to analyze the chemical composition of the plumes if they appear. Instruments on board will measure elemental ratios, identify the presence of organic compounds, and search for chemical imbalances that are difficult to explain through purely inorganic processes. This is how science approaches the question of life with caution yet depth, not by seeking direct answers, but by seeking signs that an answer may exist. Life on Europa, if it exists at all, would likely exist at the lowest boundary of biology, where survival is not about growth or increasing complexity, but simply about maintaining itself against a cold and hostile universe. The first condition shaping every possible scenario is the complete absence of light. An ice shell tens of kilometers thick completely blocks sunlight, rendering all biological mechanisms based on photosynthesis impossible. This eliminates nearly the entire biosphere familiar to humans. Yet Earth's own history shows that light has not always been the foundation of life. For hundreds of millions of years, life on Earth existed without oxygen, without photosynthesis, and without a stable surface. In that sense, Europa is not an anomaly, but a reflection of Earth's deep past. The most plausible scenario is life in the form of single-celled microorganisms, similar to bacteria or archaea. These organisms would not rely on light, but on chemical energy. On Earth, chemosynthetic ecosystems around hydrothermal vents on the ocean floor provide the clearest example. There, microorganisms use redox reactions involving hydrogen, methane, ammonia, or sulfides to generate energy, build cellular structures, and reproduce. This is not speculation, but biology that has been observed, measured, and studied for decades. From a chemical standpoint, Europa does not lack the minimal requirements for this type of biology. Spectral analyses and geochemical models suggest that Europa's ocean may contain dissolved salts, metal ions, and simple compounds capable of participating in energy-producing reactions. More importantly, Europa is believed to possess all 6 core elements of biology: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. On Earth, Every known form of life is built upon this framework. Even on our own planet, biology has demonstrated remarkable flexibility. There are microorganisms that live at temperatures exceeding 100 degrees Celsius, withstand pressures of thousands of bars, or survive in radiation environments intolerable to complex organisms. For this reason, it cannot be ruled out that Europan life, even if carbon-based, might use alternative forms of genetic mechanisms. DNA is an extremely effective solution, but it is not necessarily the only one nature could produce. Science does not claim that life on Europa would be DNA-free, but there is also no scientific reason to assume it must mirror Earth biology exactly. The ocean environment of Europa, if stable for billions of years, could allow life to persist for vast spans of time while evolving very slowly. Chemical energy, while sufficient to sustain biology, is typically far lower than the energy provided by sunlight. This limits metabolic rates and reduces evolutionary pressure toward complexity. In such a case, life might reach a long-term equilibrium, where the goal is not expansion or diversification, but survival within strict energy limits. If life on Europa were limited to single-celled microorganisms and never evolved into more complex forms, would such a discovery be enough to change humanity's perspective? Scientifically, the answer is yes. The existence of even one form of life not originating from Earth would be sufficient to demonstrate that life is not a singular anomaly, but a repeatable outcome of physics and chemistry under the right conditions. If life can exist in the darkness beneath Europa's ice, then many other worlds from Enceladus and Ganymede to icy moons orbiting distant planets become serious candidates as well. In that scenario, the universe is not an empty place with a single oasis, but a network of hidden oceans, where life may quietly exist beyond our sight. Europa orbits Jupiter at an average distance of more than 5 astronomical units, where the intensity of sunlight is only about 3–4% of what Earth receives. The ice shell, 15 to 25 kilometers thick above the ocean, forms an almost absolute barrier to external heat radiation. No light penetrates downward. There is no day-night cycle, and none of the familiar heating mechanisms that sustain life on Earth are present. So what has kept a global ocean in a liquid state for billions of years, deep within the cold of space? Its orbit is slightly eccentric, and more importantly, that eccentricity is not erased over time. The reason lies in Europa's gravitational lock within an orbital resonance with two other large moons of Jupiter, Io and Ganymede. For every 2 orbits Europa completes around Jupiter, Io completes 4 and Ganymede completes 1. This arrangement creates a stable gravitational rhythm that constantly pulls Europa away from a perfectly circular orbit. As a result, Europa is continuously flexed and stretched as it moves closer to and farther from Jupiter during each orbital cycle, which lasts about 3.55 days. The deformation itself is not dramatic to the eye, only on the order of a few tens of meters, but it occurs relentlessly over billions of years. In planetary physics, such repeated deformation is an ideal recipe for generating heat. Jupiter's immense gravitational energy does not vanish. It is converted into internal friction within Europa, warming the ice shell, the ocean, and especially the deeper rocky layers. This process is known as tidal heating. Modern thermal models estimate that tidal heating within Europa provides a powerful source of energy and, crucially, one that is stable over geological timescales. It is this stability that allows Europa's ocean not merely to exist temporarily, but to remain liquid for billions of years. A time span long enough for complex chemical processes to unfold. Heat does more than simply keep things warm. When generated from below, it drives thermal convection within the ocean. Warmer, less dense water rises, while colder, denser water sinks, establishing slow but continuous circulation. This turns Europa's ocean into a dynamic system where material is mixed, energy is distributed, and chemical reactions have repeated opportunities to occur. In the science of life, such circulation is essential. A completely stagnant environment eventually reaches chemical equilibrium and becomes dead. A convective environment, by contrast, maintains imbalance, and it is precisely this imbalance that underlies all biological processes. Even more importantly, structural models of Europa suggest that the ocean may be in direct contact with the underlying silicate rock layer. On Earth, the locations where primitive life is thought to have emerged earliest were not at the surface, but on the ocean floor, where hot water reacts with rock to produce energy-rich compounds. as water percolates through fractures in heated rock. Geochemical reactions can release molecular hydrogen, methane, and other reducing compounds, ideal fuel for chemosynthetic systems. From this perspective, the hypothesis of hydrothermal vents on Europa's ocean floor becomes not only plausible, but difficult to ignore. On Earth, hydrothermal systems such as black smokers and white smokers sustain ecosystems entirely independent of sunlight. Europa, judged by physical and chemical criteria, shares many of the same prerequisites: liquid water, a rocky seafloor, a stable heat source, and sufficient time. This does not confirm the existence of life, but it dismantles a critical psychological barrier: the assumption that life requires light. What life truly requires is usable energy and an environment where chemistry can persist over long periods. At a deeper level, tidal heating also affects the ice shell above the ocean. Upward heat transfer reduces the viscosity of ice in certain regions, allowing the shell to deform, fracture, and reorganize. This not only explains Europa's young and dynamic surface, but also suggests that the ocean beneath is not completely isolated. Europa does not promise life forms appearing clearly in front of a camera lens. The Europa Clipper mission is designed to carry out a cautious yet decisive task: to verify whether the intersection of liquid water, tidal energy, and essential chemical components truly exists beneath the thick ice shell. If these three elements converge, Europa will no longer be a vague hypothesis on an astronomical map. At that point, even a single biosignature, even an indirect one, would be enough to redefine humanity's place in the universe. Earth would no longer stand as a lonely exception, but as one among many worlds that harbor subsurface oceans. Europa would become compelling evidence that life does not necessarily require sunlight. It can quietly emerge and persist in cold darkness, hundreds of millions of kilometers away from its parent star. And if life truly exists beneath Europa's icy crust, a larger question will confront all of humanity. How many other invisible oceans are quietly drifting through the brilliant expanse of space, waiting for the day we become wise enough to see them?
worlds. While Earth is defined by its rocky mantle and iron core, the much smaller Europa is dominated by an ice.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.